In this video, we're going to talk about eigenvalues of triangular matrices. So I want to begin by stating a theorem that we actually stated in the last section, but I said that we'd kind of defer the proof to this section because it'll be a little bit easier to do now. Okay, so the statement is that the eigenvalues of a triangular matrix are the entries on the main diagonal. Okay, so let's prove this. Okay, so in our proof, in the proof that I'm going to give, I'm going to assume that A is upper triangular, but it'll turn out that a really similar argument will work when it's lower triangular. So if A is upper triangular, it'll look something like the following. It'll have some diagonal entries, A11, A22, up until the last diagonal entry, I'll call it ANN. And then the things that are above the diagonal are allowed to be arbitrary. So above the diagonal, we could have anything. But below the diagonal, well, we have zeros everywhere. Okay, so when I write this large zero, that doesn't just mean that there's one entry here that's zero. That means that everything underneath this diagonal is zero. So it's really common notation, matrix notation, to indicate stuff like this by putting a big zero in a certain section to indicate, oh, everything in that part of the matrix is zero. Okay, so now let's find the characteristic equation and solve it. So if I look at A minus lambda I, well, what'll happen is I'll end up subtracting lambda from each of these diagonal entries. So the diagonal entries would be A11 minus lambda, A22 minus lambda, until the last one, which is ANN minus lambda. And then the things that are above the diagonal stay the same. So I'll just write star. Star just represents there's something arbitrary. And the things below the diagonal stay the same. So they're all still zero. And now let's compute the determinant and then set it equal to 0 and solve our characteristic equation. So if I compute the determinant, well, this is upper triangular. This is upper triangular. And we had a key result about what the determinant of a triangular matrix is. The determinant of a triangular matrix is just the product of all these diagonal entries. So I got to take all these diagonal entries and just multiply them together. And that's going to be my determinant. So we get A11 minus lambda times A22 minus lambda, up until the last one, ANN minus lambda. So I need to set this equal to 0. In doing this, we get that lambda, the possible values of lambda, the eigenvalues are A11, A22, up until ANN. Okay, and that is what we wanted to prove. We've now shown that the eigenvalues of this matrix are these diagonal entries that we started with, A11 up until ANN. So I briefly just want to end this proof by just commenting on, well, what would this look like if it was lower triangular? So for a lower triangular matrix, so lower triangular matrix looks like we may have some stuff either on the main diagonal or below it. And then the things above that main diagonal are all 0. What we would do is we would use the transpose. Okay, so somewhere in the proof, we would end up using the transpose to turn our matrix into an upper triangular matrix. And once it's upper triangular, we can use our theorem about what the determinant of an upper triangular matrix is. Namely, that it's just the product of all the diagonal entries. Okay, so it might be natural at this point to wonder, wait, if I have a matrix A, I can always row reduce it. I can always row reduce it to echelon form. And echelon form is always upper triangular. So could I just find the eigenvalues by row reducing my matrix, putting in the echelon form, and then looking at the diagonal entries of that? Okay, so next I want to state a warning about that specifically. So the warning is, if we want to compute the eigenvalues of A, we must solve the characteristic polynomial using the original matrix. So we have to use the original matrix and not a reduced form. Okay, so the reason is that row operations, so I'm just going to call them row ops for short. Row operations can change the eigenvalues. So I'll give one example, but it turns out pretty much every row operation can change the eigenvalues in some cases, in certain examples. So let's say A is the matrix 1, 1, 2, 2. Let's say that was our matrix. And let's say we row reduced it to a matrix B. So to row reduce this, we'd probably do negative 2 times row 1 and add that to row 2 and insert that into row 2. And that would zero out the second row. So we get 1, 1 and then 0, 0. And it's really easy to see what the eigenvalues of B are because B is triangular. It is upper triangular. B is triangular. So the eigenvalues of B, which I'll call lambda sub B, are just the diagonal entries, which are 1 and 0. For A, it's not triangular. So I could use my characteristic equation. I'll do A minus lambda I and take its determinant. So I'm going to write these vertical lines that indicate determinant. And A minus lambda I would be 1 minus lambda here, 2 minus lambda here. So I subtract lambda from the diagonal entries. The other entries, the 1 and the 2, stay the same. So I need to set this equal to 0. Okay, and if I compute this determinant, first I multiply the 1 minus lambda times the 2 minus lambda. And that'll give me lambda squared minus 3 lambda plus 2. And then I subtract what I get when I multiply the other two sort of opposite diagonal entries, the 1 and the 2. So that gives me minus 2. And this is equal to 0. So the 2's are going to cancel. And then I could factor out a lambda and get lambda times lambda minus 3 equals 0. And at this point, I know what the eigenvalues of A are. So let me just call them lambda sub A. So they are 0 and 3. But notice that these are different. Notice that these are different. The eigenvalues of the reduced form, this triangular form, are not the same as the original matrix that we started with. And in general, that can happen when we do row operations. So here I did a row replacement, but it can also happen with the other row operations, where doing them can change the eigenvalues. So we definitely want to be careful about that.